Thank you. I'm embarrassed by all the praise, but I will carry on nevertheless. And let me say again that this has been a really interesting conference. I'm so happy that I was able to participate and listen to all the talks. I've learned a great deal. And I have some people I'm going to follow up on, and maybe we'll do some work together. So I'm looking forward to that as well. So let me just start, and having Hamid's talk go before mine is perfect, because I'm in some ways, of course, philosophers, we always disagree with ourselves the next minute. So there are differences, but there's a lot of similarities. So let me start by just giving a brief outline. What I'm going to do in 30 minutes is, of course, I can't reference everybody or give you all the details, but I'm going to do some rather present some arguments. I want to start by just situating where these views come from and the work that I've done in terms of the background assumptions and strategies for how to answer a question like, are emergent phenomena real? I'm going to look at the question about bottom-up versus top-down inferences to the reality of phenomena, introduce what I'm suggesting as a third way in terms of interactionism or affordances, look at a particular case of emergent robustness, and robustness means a lot of different things. I'm talking about actually the robustness of biological systems, although not just biological ones, and talking about within science do we actually establish that something is real. So that again is in this direction of using what our scientific practices are to try to understand when we're justified in claiming that something is real. And that will include looking at degrees of stability and reliability. And then I'm going to conclude, and Olympia might find this networky thing attractive, about what it is to interactively weave the web of belief. So that's a lot to say, so let's get going. All right, so here's I'm not going to talk about all of this, but my general strategy in philosophy of science has been to look at all of these features of the scientific enterprise of getting knowledge about the world, both what kinds of ontological assumptions are both required and permitted, what are the epistemological aspects, what are the kinds of representations that scientists engage with that are supposed to describe what we believe the world to be like, as well as looking at the upshot for those in terms of scientific practices. So the key parts of this, I'm a pluralist. I've been I'm an obnoxious pluralist. I think most things are pluralist, except my view is correct. And I've lately turned to looking at perspectivism, which is, I think, a feature of the epistemology of the pluralism that we find in scientific practice. So in the epistemology, lane, the most important things for this talk have to do with all scientific representational models, whether they be linguistic, mathematical, simulations, what have you. All of our ways of describing the world that we use to predict, explain, and intervene in the world are partial. They all leave things out. And the flip side of that is that all scientific representational models are perspectival. That's what's encoded in what's left in. The perspective that they take is to identify maybe a level or a scale or a granularity, whatever. I'm deeply anti-completeness, and so it's the partiality and perspectival character of the representations that plays a role. How do we know what's correct if you have multiple representations? That's the pluralism. Well, models can be more or less accurate. That's how they accommodate accepted empirical data, but they can also be more or less adequate. And this is where, given that there's no one complete model that can take on describing everything that there is in ways that are relevant to everything we want to do with them, we make choices about which model is adequate to the purposes. And the example from the talk earlier, Kate and Alex, is that I'm not going to complain about the let's say, the coarse-grained description of protein biology. But if you think about proteins, there's many different ways you can describe them and model them. You can model the proteins. Let's just think of the COVID-19 protein, the SARS-19 protein, that, we know it has, the virus, it has proteins that allow it to infect, to enter into other cells. We can say it has cell invasion properties, but and that level of granularity will tell us something about what it can do. But it turns out, in a paper published April 30th this year, shows that in fact the spike protein tells us how it invades other cells, but the spike protein, that particular structure of proteins on the capsid of this virus also tell us why it's it affects the vascular system, and it's not just a pulmonary disease that arises. So depending which granularity that we have to describe this phenomenon in terms of is going to be directed in part by the goals we want to solve, the problems we want to solve, the goals we want to do. So the big thing I'm going to talk about is the last, and these things don't perfectly line up. I'm constrained by the representational structure of PowerPoint graphs, but on the bottom is what I want to introduce is what I'm going to defend is that when scientists establish what is real, right? What we can say is real, let's put it that way, by co-constructing that through the interaction of a framework, a perspective, of philosophical assumptions, and experience through experiment or observation. So the ontology, I believe in compositional materialism or physicalism. I've been known to say that physicalism doesn't entail physicsism. I'm anti-reductionist, physics being in the representational category. The real phenomena have causal effects. That's what I'm going to take to be one of the signatures of being real. But I'm going to introduce something about Gibsonian affordances. You'll learn what that is in a minute, to try to show how establishing what is real involves this co-construction of what the causal and the representational. So let's get to that. Let's just start with Bogan and Woodward, who give us a frame in which to make these points. They made a distinction between phenomena, which are detected through the use of data, but in most cases are not observable. So phenomena are supposed to be the things that are real in the world. They have stable, repeatable characteristics, which will be detectable by means of a variety of different procedures, which may yield quite different kinds of data. So how we establish evidence for realism, when do we have a real phenomena? Are emergent phenomena real phenomena? Is that can we establish their reality? One way to do that, if they are, is that they have to have a certain kind of stability, and that in conjunction with having reliable detectors in the experimental sense will lead to convergent data. Now, this evidence for the convergence of experimental data for realism is well known from its think of Perrin's 13 different experiments for Avogadro that gave you the same pretty much measurement for Avogadro's numbers that was supposed to be taken as one of these classic cases in the history of science for defending the realism of atoms, for that this was really important. Atoms were unobservable, but the fact that he could get this convergent data meant that they had the same. Again, I don't like causal powers, but the same. There was something causally interacting with the different kinds of experimental equipment to give you this data, and that was evidence of what this thing was. That there were atoms, right? So Bogan and Woodward defend the realism of phenomena, unobservable phenomena, in terms of and the difference between data in this way. Now, this is this way in which theories, if you like, theories of the phenomena are tested against the data. I think involves the way in which I've been interested in experiment lately, the way in which experimental practices and theoretical practices jointly are required to establish what the reality of the phenomenon is what are the kinds of inferences that we can make from these different locations, if you like, in this representation of the practice of science. Again, making the distinction between data and phenomena was at least some improvement over the if H and then O thin logical representations of what the experimental practices were that were going to give us the grounds for determining what was real or what theoretical theories were we should accept. And so the theory or the model predict and explain phenomenon on the Bogan and Woodward case. The data from the experiment, the phenomenon is what is supposed to be causally related to the data that we acquire from an experiment, right? But I won't go into all the details, but just say I support the Suppy view that it's models all the way down. We're always comparing models, or the Geary view that we're always comparing models of the data and models, interpreted models of our more abstract, perhaps mathematical structural relations, the representational model, the interpreted model that attaches to this phenomenon, right, is compared with the data, the model of the data that is extracted or inferred from the causal interactions that are engaged within an experiment. So data and phenomena give us different, so I'm interested in what how does experiment give us grounds for establishing the realism of a phenomenon. So one question you might want to ask, and this is in some sense inspired by something Ajahn Chakravarty has said, which is that we need to know what are the inferences from what and to what. If we want to know, if we want to say that we have something that's, we have a case of evidence for the real reality of some phenomenon. So we can look from data to phenomenon, and Bogan and Woodward's example is lead. So I just filled out the details of the lead example. You do a series of measurements of the melting point of lead, and you see this distributed data points, and you have to clean the data. So there's a lot of assumptions going into both theories of the instrument and theories of the character of the data that give you the grounds for inferring from the data, right, that the melting point of lead is 327 plus or minus 0.04 C, right? Now, we also can infer from what to what. Okay, so we might infer from that, so sets of experiments that that's the real property of lead. We can also do it from top down. The theory to the phenomenon makes a prediction, and I don't know a whole lot about this, but there are, you can, from first principles, if you like, talk about melting of metals and thermal motion of free electrons, and with putting in the right kinds of initial conditions, you can make the same kinds of predictions about what should be the melting point of lead, right? And you can test it by doing the experiments. Now, what Chakravarty says is realists face, and this is a quote, face an apparent dilemma. The thinner their interpretations about what's real, the easier realism is to defend, but at the cost of more substantial commitments. Whereas the more substantial their interpretations, the more difficult they are to defend. I'm a very thin realist. And I'm even thinner than causal powers realism, as you'll see in a little bit. So what are we inferring to? So we're inferring from data, we're inferring from theories. Do we just read off what's real from our best theories, which is one's top-down strategy? Do we read off what's real from the convergence of data from our multiple experiments? That's a bottom-up approach to realism. And are we trying to infer something minimal? There's something exists that causes this data pattern, right? Or something more substantial, the precisely described relations and properties exist that cause the data pattern. And you see these different top-down, bottom-up approaches are associated often with these different minimal or more substantial accounts of what it is to claim something's real. You get entity realism, for example, from a kind of minimal version, whereas I can read off exactly what the world's like from my best scientific theory. So this bottom up and top down models also track sometimes other, this is another filling that out. Causation is the foundation of justifying what's real, right? And causation is what we engage, what we do when we do experiments or even observations. And real phenomena are those things that cause our experience and generate data in different types of experience. And we infer the real phenomena from the data. Whereas the top down is that structural relations are the foundation of what's real. This is one version of it. And real phenomena are isomorphic to the mathematical relations in our best theories, and we infer the real phenomena from our theories. So what are we supposed to do here? Chakrabarty says, you know, things are either top down or bottom up, right? He suggests that they're either top down or bottom up. And what I want to suggest is surprise, that they're both. You need both. You can't just do top down. You can't just do bottom up. In order to establish what's real, or what we're entitled to say is what's something about what's real, if you look at scientific practice and you'll engage your philosophical analytical methods, I will argue that you need both. And I'm going to show that through an example. But here's the approach that I think I'm working on filling out the details to, that I think captures this you need both kind of sentiment, that real phenomena are things that are sufficiently stable, okay, to afford both detection and representation, okay. So it's pluralist and perspectival, it's top down and bottom up. And I am inspired by some of the work from an ecological psychologist named J.J. Gibson, who said affordances are properties taken with reference to the observer. And here's just his, in 1977, I like this quote, and I'm going to modify it for my purposes in the next slide. But he said, the affordances of the environment are what it offers the animal, what it provides or furnishes, either for good or ill. The verb to afford is found in the dictionary, but the noun affordance is not. I have made it up. I, J.J. Gibson, have made it up. I mean by it something that refers to both the environment and the animal in a way that no existing term does. It implies the complementarity of the animal and the environment. The translation of that for me is affordances are properties, entities, or structures taken with reference to the conceptual framework, right? Not just the observer. The affordances of real phenomena are what they offer the scientists, what they provide or furnish to experiment and representation. I mean by it something that refers to both the causal properties in nature and the representational framework of the scientist. It implies the complementarity of both in establishing what's real. So what I want to suggest is that you can't really infer anything from that which is a causal interaction. You have to have a representation of it. You have to have assumptions about what it is for something to be a cause. In order to even do bottom-up inferencing to inferences to what's real, you need to have some forms of representation. That's arguments already in Duhem. So this is not new. I'm a big fan of Duhem about the translations that are required to take the result of some causal interaction, some numbers on a detection device, and turn that into evidence for a theory. Obviously, you have to make connections with that. But in addition, you need to also have some account, a theory of the phenomenon, and a theory or an account of what causation is in order to do any of this. Okay, so Woodward's, let's look at Woodward's account of causality, since bottom-up realism, what they seem to be describing in the data and phenomena work, requires the causal stability of the phenomenon across different experimental apparati, or at least one. C causes, we all know the Woodward stuff. So I won't, I'm not going to go into this. I'm just going to say that Bogan and Woodward say that data is evidence for phenomena, and you interpret that as if the experiment is reliable, then the phenomenon the experiments experimental setup causes the effects that are recorded as data. So you need to have reliable experiments, not just any old mucking around is going to give you the grounds for inferring that you've got a real phenomena. But what's the relationship between the reliability of the experiment and the invariance that's required for the causal explanation? Invariance is the kind of stability, as we know on the Woodwardian view of causal invariance. It's not universal causation. It doesn't have to be that it has the same upshot in every possible context. It just has to be invariant over some level of variable changes in order for it to be causally explanatory, causally predictive, and hence a cause. Okay, so he's already has a particular view about causality, that invariance is scope limited, it's not universal. And so that's, then we want to ask, okay, given that notion of causality, what kinds of inferences can I make from experimental data to what is real? Okay, so are emergent phenomena real on this kind of picture? So I'm going to look at just one one example of emergent phenomena. Something's called robustness. It's a property of a system that allows it to maintain its functions against internal and external perturbations. Just footnotes, robustness is always robust relative, right? It's not nothing's robust to core, but I'm not going to deal with that right now. But robustness, it comes in degrees. It can be robust against more or fewer perturbations. It can be robust against these perturbations, but not others. Think about proteins. Structure is robust against within certain temperature ranges, but not beyond those, where you they will denature or unfold. If you heat up a protein too much, it'll lose its three-dimensional structure, etc. But it is robust against those perturbations. And let me look at an example I've talked about in a different context, just to make the point. You might think of that, you know, if the kind of invariance, the Woodwardian invariance picture of causality is if I wiggle this variable and it changes something down here, right, then it's a kind of, that's kind of the meaning of what it is for this to be causal, that if I could intervene on it and remove it or change it, then I would see a change in the consequent effect. This is a kind of perfect Mills method, a Mills method kind of notion about invariance, and knockout experiments were an implementation or realization of kind of Mills method. If you could knock out a gene, which it turns out not to be so easy, and you could tell, and you could then look at the resulting organism that had a double knockout, you could infer what the function of that gene was in the phenotype of the organism. Okay, now it turns out that like 30% of knockout experiments give you a really pretty much the same organism you had before, right? Okay, and there were two kinds of inferential responses to this fact, that there were, you knocked out these organisms, but you didn't get a change in the phenotype. One is like, oh, I guess that gene didn't do anything. Okay, that was one. I won't give you the quotes, but that was one response. We thought it did something, but it doesn't because we knocked it out and we don't get a change in the effect. We've wiggled the variable. Others have said, in fact, Mario Capecci, who invented knockout experiments, said you just didn't do the experiment correctly, right? You didn't do it right, or you would have seen the effect of that gene on some phenotypic trait. Okay. A third option was proposed. This is from Ralph Greenspan. 5 minutes. Okay. The third option was that maybe the network itself was robust and it reorganized in response to the internal perturbation to satisfy the same system level function. Okay. So let me go faster. And this thing about robustness has been one of the founding ideas behind systems biology, where in fact we have to understand the networks. Okay, so how stable must a phenomenon be in order for it to be detectable, support, and real? Okay, so we might think that emergent phenomena like the one about the flexible genome is highly context dependent, or some of the things we heard from Hamid last time, that some of the behavior is very highly context dependent. What this gene does depends on what the context is, right? We might think that the other things have high probability dependence, holds for most cases, like the ideal gas law, but not some cases at extreme temperatures. Or we might think that it has to be universally dependent. Maybe the melting point of lead is pretty much universally dependent. So you can see that how stable a phenomenon, stability can come in degrees and kinds. So how stable it is, varies. What are the degrees of convergence? What degree of convergence constitutes reliability? How stable do my interactions with it have to be for me to consider that to be reliable data, right? I might have difficult to repeat unique experiments, right? I might have multiple data types that give the same value. I might have all data processes give all the same value. It's that the kind of notion you have of causality, if causality has to be the same answer in every case and you get results that are different, what are we supposed to infer from that? If the data from different types of experiments converge, then infer the phenomenon is real. That's the old story. That's the Perrin story. That's what we all think as the way to infer from bottom up. If the data from different experiments diverge, then what do we infer? Okay, what are we supposed to say if we get different results from our experiments? Well, one of the more experiments is not reliable. That's the Mario Capecci, or there is not a real phenomenon. That was the other response to the knockout experiments. I want to suggest that that's not the case, that there could be a real robust phenomenon that has different causal effects in different contexts, and that if we have an emergent phenomena, the same kind of inference structure cannot be required for us to establish its reality as if we have some kind of universal context insensitive phenomenon. So reliability, causal stability, and realism all hang together. Causal invariance comes in degrees. You don't need universal exceptionalist invariance for causal explanation. Phenomenal stability comes in degree, hence the invariance, the causal relationship between the phenomena and the data also comes in degrees, right? You don't need complete or even wide context sensitivity for reliability. So we have to match up to be able to know how to make an inference. We have to match up the correct account of reliability with what the correct account of stability is for the phenomena. So what counts as reliability in the data, which is what we need to infer realism, is dependent on the degree or type of causal stability of the phenomenon. Reliability is always reliable for something, not reliable to core. This data is reliable for this kind of inference. A conceptual framework of causation and a theory of the type of the phenomenon is required to specify the appropriate form of reliability for data to support phenomenal realism. So what kind of data or evidence for real emergent phenomena? On the Bogan-Woodward account, reliable convergent data. Reliability is supposed to be independent of a theory of phenomena for them, only informed by theories of the experiment. Divergent data would then lead to no phenomena or artifact, or it's an artifact. For me, reliable convergent or divergent data, that's other stuff I'm working on, I'm not going to say now. Divergence can be due to different perspectival partiality or dynamic context-sensitive causal behavior. So the standards for reliability are relative to the kind of phenomenon, if it's emergent, robust, nonlinear, and to our theory of causation. Does it have to be universal? Can it be scope-limited invariance? So conclusion. Real phenomena are sufficiently stable to afford detection and representation. There are different types of phenomena, there's different degrees of stability, and there's different criteria for reliability. Real phenomena are co-constructed. What we think is real is co-constructed jointly from the bottom up, from the causes, from the top down, from our theories, within a philosophical framework of what we mean by causation. And that's it. Thank you.